Can people see my screen, or could people see my screen?
Yes.
1 second. So people can see the slides and hear me?
Yes.
Perfect. So today, a few of us are going to be talking about a project that's been largely run from our group with quite a bit of collaboration from others here on generating initial data for binary neutron stars using Lorene. It's been a joint effort. The lead graduate student on this project is Tanmayee Gupte from RIT. And we've been working with two former undergraduate students, now soon to be graduate students. Grace Fiacco, formerly from RIT, soon to be a graduate student at Montana State, and Trung, formerly from the University of Rochester, soon to be a graduate student at the University of North Texas. So since there's a whole variety of people on the conference today, I wanted to go back and talk a little bit about the basics of initial data and how Lorene works. Apologies if people have heard this before, but I figured a bit of an introduction might help, and might help explain some of the challenges you face when dealing with initial data generation. At the moment, there's not so many different formalisms in play to generate initial data within the field of numerical relativity. The conformal thin sandwich formalism, which has been around for a few decades now, combined with the assumption of a helical killing vector so that the stars essentially orbit each other, is the dominant approach used by virtually all the major initial data codes. That set of statements implies several different equations that need to be solved. Some are easier, some less so. The solutions for the general relativistic fields, the space-time metric, reduced to elliptic equations, and certainly at this stage, solving elliptic equations in space is typically the easy part of any code. Matter fields, particularly things like the density, can be described by an enthalpy equation with the neutron star surface being an isenthalpic contour in your actual code. Anytime you've got surfaces, this introduces some challenges. In particular, the density and other quantities are not smooth at the neutron star surface, which means that spectral methods codes will encounter Gibbs phenomenon errors unless you make sure that the neutron star surface occurs at a domain boundary. This is the known technique for avoiding Gibbs phenomenon. And indeed, it's what Lorene does here. And finally, when you're doing hydrodynamics, you need some kind of equation to solve for your velocity field based on some assumption of what the velocity field of the neutron star should be. Lorene employs a potential-based approach, especially for irrotational configurations, that can either work with co-rotating stars, which is in some ways the easiest case, or irrotational stars, which is thought to be the physically motivated case. Right now, when you're using Lorene, and we'll show some plots and generation of data coming up shortly, there are basically two problems out there that haven't been fully solved and implemented, and certain things that are not particularly a challenge. One challenge has been actually implementing systems to solve for neutron stars with arbitrary spins. The formalisms are out there. They've been out there for slightly over 10 years now. But there are no particular wide-scale implementations describing neutron stars with completely arbitrary spins. In fact, depending on how big the spin of a neutron star is, and the natural scale to compare it to would be the angular velocity of the binary itself. If the angular spin of the neutron stars is significantly less than that, you might consider some kind of more perturbative method where you kind of take a base spin configuration, likely irrotational, and kind of by hand add on some irrotational spin, add on some spin on top of that as a possible format. The other missing piece from initial data formalisms that hasn't been widely implemented would be how to impose a magnetic field in a self-consistent way into the neutron star configurations. Again, there might be different ways to handle this problem. If the magnitude of the field was small enough so that the magnetic pressure was relatively small compared to the gas pressure throughout the main volume of the star, you could again see some kind of perturbative technique working pretty much okay, where you would simply add in a magnetic field but neglect its pressure contribution to the neutron star structure. The one bit of physics that's less of a challenge to implement is any model involving the equation of state. So long as you can write down the pressure as a function of density, and typically assuming that that function is monotonic, you can basically implement just about any scheme you want without a great deal of complication. There's not any strong assumptions in Lorene about what the equation of state really has to look like. There's a number of different models that can be used to describe equations of state. It's a matter of choosing the one that best meets your needs. So I've mentioned Lorene several times. That's the code we've been using. It's worth talking a little bit about what it does. Lorene is a code that's been around, again, for about 20 years. It's put out by the group at the Observatory of Paris-Meudon. Publicly available multi-domain spectral methods code. It's basically an elliptic equation solver that has been specifically used to solve quasi-equilibrium binary configurations in GR. The brilliance of Lorene, besides it being a perfectly good and workable code in many, many ways, is that they realize that in order to deal with neutron stars, you need to be able to deform an ellipsoidal surface to match up with the boundary of a neutron star. So in particular, Lorene will adapt the location of its spheroidal coordinates so that there is some domain that matches up exactly with where it figures the isenthalpic surface, defining the surface of a neutron star, should be. This allows you to minimize Gibbs errors quite substantially and is basically critical for generating good initial data. If you fix the geometry and the neutron stars don't conform, these Gibbs errors will forever be W as you try to use that initial data in a dynamical scheme. Lorene actually splits all fields into a component centered on each star. As we'll see in a figure coming up in a few slides, it's not one set of domains in one half of the space-time volume and one set of domains in the other half. There's two different sets of nested domains, each of which covers all of space. Every point in space-time finds itself in two different sets of domains. And fields are divvied up so that there's a component of a field that's in some sense seen as centered on the first star and seen as centered on the second star. This creates some challenges, in particular if you want to consider not just neutron stars, but also black holes, in the sense that for the fields centered on an object, they're well suited to deal with any kinds of non-smooth behavior that comes from the neutron star surface, or for a black hole, an excision surface around the horizon, where you apply boundary conditions. But there's always the challenge that the other set of domains will see that non-smooth behavior coming from the other star, hopefully in a way that doesn't create problems, but it is something of a challenge for these methods. The other important thing to note, Lorene being a spectral methods code does not handle cusps well as you take neutron stars near the tidal limit. You get high frequency noise when you try to model a non-smooth function with smooth functions. And I will now hand off to Tanmayee, who's going to continue on for a little while.
Hi, I am. Can everyone hear me?
Yep.
Okay. So I'll be talking about how to launch a run on Lorene, and the way to do it, you basically need initial parameters to tell what your configuration should be. You need two sets of files to define your configuration. The first is par EOS, where you specify the equation of state model for both the stars 1 and 2, and the second one is par grid, where you define the grid dimensions and the domain radii. um, the grid sizes are not arbitrary. They are FFT-like condition on certain parameters. And so it is a two-step approach, which assumes that you have an implicit knowledge of the sequence of the isolated neutron star models for a given equation of state. For example, the relationship between the central enthalpy and baryon mass. So the first step is calling the routine called init_bin, which is short form for initial binary. The parameter file for that module is par_init.d, where you give what the separation between the two stars should be, which is just used for superposition. And the second one is what is the central log enthalpies of each of those stars. After you run the initial binary routine, there is the second routine, which is called as col, which is again short for coalescence. And the parameter file for that is parcol_mass scan.d, in which you need to specify what is the revised separation between the two stars and what are the final baryon masses that you want for your configuration. Could you go to the next slide, please? Okay, so you can even, once you finish running both the routines, you can use Lorene to plot what your initial data configuration should look like. For example, in the top image, you can see that we have plotted the log of lapse, which is the gravitational potential for both the stars. And the green lines are the domain boundaries. As Josh had mentioned, both the set of domains fill all of space, and in order to calculate each field in split fashion, which means that the other set of domains sees the neutron star surface, and there will be unavoidable Gibbs phenomena errors. In the second image, we have plotted the velocity field, which is given by the white lines, which also can be used for plotting isocontours of global system. And the cuspier the surface, the more one encounters high frequency noise. So this is the way you can view how your initial data or what different kinds of fields should look like on your initial data configuration. Could you go to the next slide, please? Okay, so there were so Lorene uses a complicated relaxation scheme, and there are 6 different relaxation parameters for different field components. And it had multiple failure modes, and the safest parameters for which we could get stable configuration were low mass neutron stars and the configurations which were well separated, but not too separated, because as the outermost domains have coarse resolution. So one of the issues that we faced was while getting mass ratios close to unity, that is mass ratios which are not basically unequal mass ratios. And the current routine used to locate the rotation axis relies on an unstable secant method implementation. And so the function would potentially diverge. And the way we fixed that was by taking the reciprocal and numerically fixed it. So now we can run configurations that are close to almost 1.5 mass ratio. On the right hand side, the lower image shows how the center of mass would wander off, and which is what was causing the problem with the initial secant method that we were implying. But the fix works. Could you go to the next slide, please? Oh, it didn't show. Oh, it showed. Never mind. So another fix that we used was for getting high mass binaries, and so Lorene's relaxation scheme makes it difficult to relax configurations extremely slowly, because some quantities are recomputed from scratch at different time steps, and it is best if we assume that things will end up undamped. So the way we use so what we did is we built a mass stepping scheme in which we start at 50 kilometers. For example, we would start the configuration at 50 kilometers at low mass, and then we would decrease the distance between the stars to 45 in steps of 5, and slowly increase the baryon mass by using stable configuration from the previous time step, you could say, or the mass step. And that way we were able to get high mass binaries, as shown in the graph on the right hand side of the slide. Um, so we were able to get stable result beginning from low mass configuration, moving inwards to the desired radius, and then slowly increasing the target mass of the binary system. Could you go to the next slide? Oh, I think this is Josh's part. So.
So as I mentioned before, Lorene doesn't have a lot of assumptions built in about the equation of state. They've actually been able to code in any number of different options that can be used. The simplest models are polytropic equations of state, where the pressure has power law dependence on the density. But it can handle any number of other cases as well. One of the widely used models within the field, certainly one that makes it easier to compare to, are piecewise polytropic equations of state. The leading models typically involve 3 different polytropic segments for the high density regime, where the convention has become to allow piecewise polytropic segments to change character at 2 reference densities, 10 to the 14.7 grams per centimeter cubed and 10 to the 15th grams per centimeter cubed. That actually gives you a 4 parameter model. There's 3 polytropic indices, as well as some kind of reference pressure to set the overall vertical scale. And typically you assume that once you reach sufficiently low density, your model intersects with some kind of fixed crust model. Now, this could be important in some aspects, but especially for initial data. You typically don't resolve much of this crust region at all. We would typically find that it occurs for something like less than one grid cell in our spectral scheme. So while there may be complicated physics in the low density region that will be important potentially for dynamical runs, you tend not to see it for initial data runs. Whereas the high density behavior is captured in these models using these parameters. And we're not necessarily advocating that this is the only choice, but it seems to be a perfectly workable choice so far and allows for comparisons with other studies in the literature. So I believe Trung is going to take over next.
Hi, everyone. Can you hear me?
Yep.
Okay. So I will be talking about the result of our project up to this point. After implementing all the fixes to Lorene that Tanmayee mentioned, we set out to generate an initial data library, which covers different piecewise polytropic approximations of a set number of equation of states, including SLY, AP3, AP4, WFF1, MPA1, MS1, and MS1B. For each of these equation of state, we cover different mass ratio of the 2 stars by fixing one star at 1.4 solar mass and varies the other star mass from 1.4 to 2.0 at 0.2 solar mass increment. And also for each of these mass ratio, we cover different separation that starts from 50 kilometers apart and decrease by 5 kilometers until we hit 30 kilometers separation distance or until a stability limit is reached. Lorene is also capable of generating initial data using tabulated EOS with built-in module. where the table format includes the baryon density, the total energy density, and the pressure, which is a lot simpler than the multi-temperature or YE format from the stellarcollapse.org website, because initial data assume that we have cold matter, where all the parameters depends on the density alone, and thus the pressure as a function of density is well defined. Can you go to the next slide? Okay, so to test the validity of our initial data, we start launching dynamical simulation of the initial data that we generated using the Einstein toolkit and Illinois GRMHD. So first we compile the Einstein toolkit using downloading from the Einstein toolkit website, plus the thorns that are written by the Parma University or the West Virginia University, using the links below, both of which have compatibility with piecewise polytropic equation of states. And then using their parameter files, we modified the parameter file with the gamma and the rho value that is specific to our equation of state, and using the input or the initial data file, which is in the format of a residue underscore whatever the mass and distance of the stars are, .d file to perform the dynamical simulation. Using the Einstein toolkit, we can also specify AH finder direct parameters, which tells the code to detect for a black hole after a set amount of time. Can you go to the next slide, please? Okay, so these two are the two movies that we were able to make with Illinois GRMHD code and the visualization software. The first video you are seeing right now is for a equal mass binary neutron star with 1.4 solar mass using SLY equation of state and the initial distance of 32.5 kilometers. And the second video that you're going to see now is for two star, one at 1.4 solar mass and one at 1.8 solar mass, using the SLY equation of state and an initial distance of 37.5 kilometers. And you can see that there is a black hole that is formed at time 656. For the first run that we did with the equal mass binary neutron star, we were not able to find a black hole because the code stalled right before the last frame of the video, and we think that it might be because the resolution that we used was not high enough for this particular simulation. Okay.
And that's the final slide.
Yeah. Thank you for your attention.
Yeah. And we'll be happy to answer questions, sir.
Okay, thank you very much. I guess we should start with Beanie.
Hi, thanks. I just had a quick question. When Tanmayee was showing kind of the sequence of how to relax into the binary data when kind of reducing separation, she said it was there are stability issues, but I was wondering, and they generically were better if they were smaller neutron star masses. But I was wondering, is there a large sensitivity to the equation of state? Would harder equations of state yield more stability when you're going through this procedure, or does it really matter?
I think it probably would. Our experience is just that as you get up to the maximum allowed mass, because Lorene is difficult to relax extremely slowly, it's difficult to underdamp it during a relaxation sequence. the closer you get to the mass stability limit for a given equation of state, the easier it is to accidentally cross through an unstable region of phase space and have things crash on you. But in some sense, the safe mass to change in distance first before you then fix your distance and increase mass towards the target one, that safe mass does scale along with the maximum mass allowed by the equation of state. Stiffer equations of state, you can use larger masses for kind of your reference model as you evolve towards your desired state. Softer equations of state, you want to start with lower initial masses to keep things nice and calm, in a sense. But one thing we found was that it's easier to get the distance right first at low mass and then increase the mass. Trying to go the other way tended to lead to instabilities and code crashes, where you try to take heavy stars and walk them inward.
Thanks.
Okay. Bruno, do you have a question?
Yes, just a technical question. Lorene provides some codes to compute the initial configuration for binary neutron star. Which one are you using? I'm asking because I was used to use a code. I was using a par file called par call and not par, I don't remember the name, called mass sequence or whatever.
Right. So we've modified their driver routines, but that was our starting point. We're using the Cole, the Cole routine that comes with the Lorene code as a starting point. These are let me get this right, the French named binary neutron star thorns. It's not thorns, sorry. Modules, not the English named binary modules that came later. But basically we took their Cole routine, coalescence, and modified it to explicitly build in this mass scanning feature. So the guts are their Cole routine, essentially being looped over to allow other parameters to change at the time.
Okay, thanks.
But the underpinnings is their Cole routine.
Okay, thanks.
Okay, are there any other questions? We do have time for another question. Okay, if there are no other questions, I mean, thank the speakers, and